Now I want to illustrate the animated graphical profiles with this classic example where we have a pump pumping through a pipeline up to an elevated tank. The pump trips, which will quickly lower the pressure. You have a check valve. This will shut. You'll get a negative pressure wave going down the line, and you'll have often have high pressure spikes forming and cavitation in the system forming. Various types of surge protection, such as a surge tank or air vacuum valves, can be evaluated using this graphical profile animations that we have. Now the first presentation will be with no surge protection. Again, the pump's going to trip, and this is a hydraulic grade line. This indicates how high the pressure is at all points along the pipeline. And when the pump trips, this will drop down, and you'll see the effects of the pressure surge as you go through this analysis. So let's take a look at this. You see the pumps run down, the check valve is shut. You're seeing these pockets of cavitation, and you'll see spikes when these cavities collapse. Now at the end, you have an envelope of the hydraulic grade line or pressures. It spiked up here to about 150 psi. All along the line, the negative pressure has reached a value of minus 14 psi, which is cavitation. So the cavitation is formed all along the pipeline, and in many cases this is unacceptable. Now I want to look at the same transient problem with some surge protection in the form of air vacuum valves. These are valves that admit air into the system when the pressure drops and expel it when the pressure goes back up. They're nominal air valves, which mean they have a single orifice for admitting the air and expelling the air. So let's see what happens when we trip the pump. We trip the pump, the pressure wave goes down. Now I want to stop for a minute. You see that all three air valves have been activated, and there's been no cavitation form in the line beyond the original reach. So at this point, the air valves have been successful in preventing downsurge. But I want you to take a look at this when we start up again. We'll see a phenomena called air slam. Once this air is expelled, if the water columns come together too rapidly, you get a large pressure surge, which can initiate additional transient problems. So let's look at this. You see when the air's out, you get this pressure surge, and now you start seeing cavitation form in intermediate points. So now the analysis is complete, but we've had high pressure spikes and cavitation all along the line. So these air valves weren't effective in reducing the high pressures and the cavitation. Now there are anti-slam air valves that would be more effective for doing this. Okay, now we want to look at the same situation with a surge tank in place. While the air valves provided what I call passive surge control because they responded to the downsurge, the surge tank provides what we call active surge control because it operates in such a way as to eliminate the surge rather than to react to it. When the pressure drops, water comes out of the surge tank and replaces the water that's lost due to the pump trip, and therefore can reduce the amount of transient pressure that we get. So let's play this and see what happens. You can see the pressure drops, the surge tank is providing water. It was initially half full, and now the water surface oscillates up and down. We actually run this for a full minute, 60-second simulation. Now, the interesting thing here is that the envelope of pressure is contained between this upper limit and the lower limit. Let me go back to the initial hydraulic grade line was this. So we have very little additional pressure, and the pressure drop was very much contained. So the surge tank has been extremely effective in eliminating the surge problem.